Back, and we are finally at the day we've all been waiting for, or at least people that like chemistry have been waiting for, which is finally making polymers using direct exchange and acid chloride polymerization methods. So remember, these are all still, we're continuously talking about step growth. After today, in this video, we will finally talk a little bit about chain growth reactions and kind of what can happen there. So we are going to make our first polymer, which is a polyester. Just remember from last time, we talked about nucleophilic acyl substitution. This is kind of the main method of attack and chemistry that we're going to be dealing with today. So remember those nucleophile attacking that electrophile, that transfer electrons, the leaving group leaving. And again, we talked about this really, really important table of reactivity. We want to be on this side so we don't have to remove reactions and use the Chatelier's principle in order to make our reaction go proceed forward and to build and basically synthesize high molecular weight polymers. So we want these, we want to avoid these, but sometimes in chemistry, as in life, we don't get what we want, so we'll have to deal with it as we do as engineers. But anyways, we're going to be talking today about three big kind of methods: direct esterification, ester exchange with alcohols, and reactions of chlorides. So there's in our notes, obviously, we kind of talk about this quite a bit, but I think the best example is to look at some polymer chemistry and see how we're going to deal, or how these reactions occur. So let's start most general with the direct esterification approach. So let me get my pen. I want to make it a little bit thicker on these slides. So what are we going to do? So in direct esterification, we are going to be reacting, again, our kind of acyl group right here, just like we did previously. We know that here the KQ is about 1, so it's not like our chlorides. This molecule is not extremely electronegative, so this isn't as electron poor as we would like it to be, ideally. So we are going to have to remove whatever the byproduct is. So in general, this R group can be kind of, again, our polymer. Same thing on this side. This is going to react, and again, this is still our electrophile. We're going to attack here, and what's going to result is that substitution, right? So our substitution event, we attack that electrophile with our nucleophile here. So it is going to attack right here, pick off one of these, and we're going to be left with, you can imagine here, this exchange. So we link R, C double bond to O, O, and then R prime. So that's what we're left over. That is our product. That is essentially like our C that we kind of dealt with previously. And our byproduct is, again, this little, let me change my color. It's this combination. That's, again, this is essentially our leaving group effectively. So these guys leave, we're left with H2O. But again, we have to remove our byproducts because this K equilibrium is so low. So this is not a good enough electrophile. We need to remove the byproduct we need to kick this guy out. Again, because of our K equilibrium constant being, basically this is D and this is A and B, we know that KQ is C, concentration of D, over concentration of A, concentration of B. So if KQ is 1, the only way we could kind of push this reaction forward, kick this guy out, we must maintain this equilibrium constant, so this guy has to increase that concentration. So that's an example of direct esterification, again, in general. So you could also have extra exchange with an alcohol, again, in general. Same idea here. So our unit here, KQ is about 1. Again, not as electronegative, this electrophile is not, or this group here is not grabbing our leaving group. This is effectively here. This electrophile is not as electrophilic as we would want it to be. We want to pull electrons away from it. So again, we have the attack that comes in here, and then this group is going to change to my blue. This group is going to bond and become a byproduct, and then we're going to link these guys together. And so again, very similar procedure that we saw on the last time, and we still have to remove this byproduct, kick it out, because that KQ is so low. All right, let's look a little bit more. And then finally, again, with our generic reactions, again, it's going to be more fun when we actually make polymers. But our third kind of step, our synthesis method in general, is this reaction with acid chloride. So When we have this group, we know our KEQ is 10 to the 4th. We're good to go. We don't need to remove byproducts. The reaction is just proceeding forward, not out of control, but very nicely. We don't have to do anything with it. And so this is a really, so this is partially negative. This is definitely partially negative, and here, really partially positive. So same thing occurs. We are going to, let me switch to my blue. This guy is going to attack in here. These are going to basically bond. Our byproduct here is going to be HCl. And again, we link our new polymer or our new material together like so. And that's it. We don't need to remove the byproduct now. The one thing, especially in biology, this HCl, that is acidic. It's going to change your the acidity of your solution. So if your polymers, if your biomaterials, if they're sensitive to basically pH changes, we might need to think about removing this, or more likely adding basically add a base to maintain the pH of our solution. So polymers can denature, proteins can definitely denature. They could fold, different pH conditions and temperature as well. So we need to kind of keep that in mind as one little kind of avenue of concern as we move forward and play with polymer chemists, because we're not chemists, so we need to be a little bit careful. It's not as easy as it sounds, but it's definitely not as hard as material science and engineering. Anyways, that's a little dig at the chemists. Anyways, so let's make our first polymer. So we're going to make polyethylene adipate. Or hopefully I'm saying that right. So this is adipic acid. This is ethylene glycol. So again, two structural units, basically two monomers. So we are going to combine these together. So again, we still kind of see the same kind of structural unit. You could basically imagine like this just being like that huge, R group previously. The one thing to note is, even though we've kind of, so let's just focus on this end here. So again, we have our acyl group. We are going to, again, attack it here. What do we know about this leaving group? OH. KEQ is very low, so around 1. So we are going to need to remove our byproducts. Yes, I could hear you all at once saying it with me. So we're going to need to remove our byproducts. So same thing's going to happen. We've already kind of circled it here in this diagram. So these are going to combine. They're going to kick off and become water, our byproduct. That's why it's sometimes called a condensation reaction. We're not going to say that in this class. But one thing I want you to notice, again, because we have basically these two functional groups, because we're, again, adding these monomer units. So the same thing is going to happen on the other side as well. So really, it's kind of 2H2O, but again, I'm not going to kind of, if you're really interested in mass balance, you could definitely write that. It's no big, no problem. But we're just kind of going to write in general that we know that those ends are going to react as well, and you're going to be left with basically this polymer. Because here's your repeat unit, and it's going to repeat X or N number of times. So this is polyethylene adipate. Adipic acid, ethylene glycol, we must remove this because of that reactivity of the leaving group, and that's it. So you made your first polymer. Congratulations. You're now officially a polymer chemist. So you could go out in the world and be very careful. Teflon, you could create chlorine gas. We don't want that to happen ever. So a little knowledge is a dangerous thing to be sure. But anyways, let's make yet another polymer. So let's make PET, polyethylene terephthalate. Really ubiquitous polymer, used a lot if you drink a lot of soda. Don't drink too much soda, but it's kind of that clear plastic. A lot of soda bottles are made out of it. TG about 80 degrees C, melting temperature 265 degrees C. Remember, this is breaking intermolecular bonds, not intramolecular bonds. TG, glassy to rubbery. So once we're above 81, we're rubbery like silly putty. When we're at 79, we are solid like a glass. So viscous, elastic. More on this once we get a little bit later on. So we want to react. So this is polyethylene terephthalate. This is your kind of terephthalate unit. Again, two structural units, two monomers. And again, similar mode of attack that we've kind of been dealing with and seeing previously. So this is our electrophile. We're going to, with this group, attack here. What do we know about that leaving group, OH? AQ is low, so we need to be removing our byproduct. These combine. They combine on the other side as well, and you're left with essentially this polymer. This is your polyethylene terephthalate that you bind. polymer chemistry in this course. Obviously, things get really, really complicated, and we're going to see an example. And there's multiple ways you can make this polymer, but kind of just keep that same mindset as you're kind of progressing through this. So one of the interesting ways you could kind of make polyethylene terephthalate in another way. So you could start with some different structural units here and combine, or actually bind. So when we look here, again, we're going to attack here, but now we have kind of this different leaving group here. This basically the CH3, which is very super low K equilibrium constant. But again, we're going to attack here. These are going to react and bond. So you're left with this byproduct that we must remove. We're going to react with this molecule in excess. We're going to see why in a second. And it's going to react here, and you get kind of this linkage. So this is not a polymer. So this is why it's step one of this reaction. Once you have this this product here, and that's why we kind of mentioned we have excess of this structural unit. So once this reacts, then it is going to react. Basically, these are going to react together. So one structural unit or one byproduct of here is going to react with another of those products somewhere else in your solution. The attack this time is going to occur, again, with all this mess. It's going to occur here. And again, same thing. We're going to bond. We're going to bring this out. These are going to be our byproducts, our group here. We still attack this guy. Still low K equilibrium constant. But this time, once we kind of do this reaction, we'll finally form PET, our polymer of interest. And our byproduct here, we don't have to remove because this, if we go back to here, was what we had in excess. So this is going to, again, bind with other, other of these structural units, and we're going to go ahead and be fine with it. So multiple methods to make a polymer. This is kind of a laborious method compared to the first method, but again, it depends on the structural units you're working with, what you're limited to in your solution, and basically what you're trying to achieve in making your polymer chain. Let's go through a couple more examples. Finally, some acid chloride reactions where we don't have to worry about. So anyways, let's make polycarbonate. Polycarbonate, PC, it is a very, very common, again, that's kind of like your plexiglass, again, transparent polymer, very, very rigid, not very ductile. Well, polymers is not very ductile, not compared to metals, obviously. But again, we have two structural units here, structural unit. We know here, this Cl, that K equilibrium, as we've noted here, extremely, extremely high, where you're going to attack here. The H and Cl are going to react, form a byproduct we don't need to remove, but if we're worried about pH, we must consider this at a base. And what you're left with, and it happen on both sides as well, is our polycarbonate. That's it. I love reacting with acids because they're so reactive, although a little bit dangerous. You could also make carbonate a different way. So if we have different structural units, again, multiple methods, but again, same procedure. Attack this electrophile, but this unit is going to be very low K equilibrium constant. Why? Super bulky, not very electronegative at all. That is going to be very, very much less than, not less than 1, but very, very low. Very, very low is what I'm going to try to say about this. But you attack, you bind, you have a byproduct, and we will definitely have to remove this to move forward and progress with our polymerization chemistry. So I'm going to do two, before we finish up with our kind of polymer chemistry discussion, we are going to make a very, very special, two kind of special materials. Nylon, not that special, but I love to tell this story. And then Kevlar, which is a very important polymer. Polyamides. So we are going to make here, what nylon is this? This is nylon. So there's 4 nylons here, 4 carbons here, 1, 2. So this is 6 carbons here, 6 carbons here. This is, we're going to make nylon 6,6. That's how you kind of count. So you count the number of carbons here. So if I react, and you've probably done this polymerization, nylon 6,6, we're going to look at it in class. Basically, it's too unfortunate we don't have to do this. We can't do this in person, but nylon 6,6, you could make nylon rope with interface polymerization. Basically, you pour these, basically a solution of this structural unit together. You have kind of this vial here and here. They phase separate, so you have basically your NH2s here, your COOHs here. And then if you grab a hook, you could basically grab the polymerization process that occurs at this interface and pull nylon rope. Now, you've probably done this in other chemistry classes before, and if you are like me, this has never worked. It's always a failure and complete disaster. You could never, the rope always breaks, it's not reactive, things are going on. But I think I found the solution. And you know the answer too as to why it happens based on your just this video and lecture. So most of the time you'll use these materials. So what happens here in this chemistry? So we know that we're going to have a similar attack that occurs here. So what's the KQ here of this leaving group, OH? Well, we know KQ is really, really low. So unless we remove water, this reaction is not going to proceed quickly. So again, we have our same attack. You have H2O, and you're left with, that's your byproduct. We've actually created our polymer. But if we don't remove water, which you usually don't do in these experiments, if you're doing nylon rope polymerization, this reaction does not proceed quickly, and your nylon rope breaks, and it's just a mess. And it's nothing ever kind of good comes from it. So I've done when I did this lab, or when we did this lab in person, I actually used some different one different material. What's the difference between the previous slide and this slide? This Cl. My KEQ now is 10 to the 4th. I'm forming this at the interface. I don't need to remove this byproduct. I get tons of nylon rope. The demo works perfect. I look like a polymer chemist genius, and you get some nice nylon rope to play around with. So I'll show you some videos. That's kind of typically how you could kind of improve that demo. So as you go on, you can kind of go back to your chemistry professor and ask him, why didn't he know about his acyl leaving group equilibrium constant? And then finally, we'll stop today after this, just making Kevlar. Kevlar is obviously used for lots of different body armor applications, but again, it's the same process, polymer. So we know here that we have this leaving group, that Cl, that KEQ, extremely high, 10 to the 4th. And we could react it with this subunit here. We grab basically one of your H's, reacts with here, there, and here. And we have our amide linkage that we've talked about previously. And then we have our byproduct HCl. You may need to remove it again if you're worried about processing or kind of the pH of this solution. Now, I said that the reaction is catalyzed with DMF and LiCl. These aromatic rings along the backbone are really, really bulky. So sometimes, and actually oftentimes when you're producing Kevlar, you need to catalyze this reaction because we need some of the unique processes or the unique behavior that comes from of Kevlar. So Kevlar is able to absorb, again, the impact of a bullet. One of the reasons is along this backbone you have these kind of aromatic rings, lots of double bonds and for carbons. So this is a really, really rigid backbone here. And we also have these amide linkages all around that allow us to do intermolecular hydrogen bonding. So that leads to kind of the mechanical properties of Kevlar as well. And these aromatic rings, though, they're really, really large, really bulky. They're really close to one another. And so to kind of improve that chemistry and move that chemistry forward to avoid any steric hindrance, you'll often kind of see this catalyze. And again, you want to produce, for Kevlar, we want ultra high molecular weight, lots of, a ton of polymeric and basically number of monomers in our polymer chain. So that's often why you'll catalyze that reaction. That's kind of the more practical application of processing. Obviously, catalysts are used a lot in chemistry, but again, in this class, I just want to focus on that acyl attack. And if you could do that, if you could do these chemistries, that's all I'm looking for. So you're now all officially going to go into the world as polymer chemists. I don't know if that's good or not. No, it's really, really good that you know this. So next time, we will talk about chain growth polymerization, and that is going to wrap up lecture 2. And then we'll get into lecture 3, and we'll get into some chain models and some other kind of fun ideal polymer chains, real polymer chains, entropic springs, excluded volume, all fun things to talk about. So we watch the video next time, and we'll finish lecture 2, and we'll be off and running. Thanks, and I'll see you all next time. Bye.